though I didn't understand a word. I have to admit that languages I learned in school were English and Latin, no French. And so during my stay here in Paris, I struggle a little. And I cannot overhear conversations. But I guess Patrick told you that this is a presentation that concerns fairly recent developments in the, well, fairly old field of boundary integral equation methods, boundary element methods, developments that I, together with collaborators, started about 10 years ago. And that yielded some surprising results and many new open research issues. But before I dip into the details, I've got to acknowledge the contribution of my two main collaborators, my two former postdocs, one of whom is sitting here. This is Xavier. And, well, I proposed this topic to him when he joined me at ETH. This was in 2007? 2009, oh, less than 10 years ago. And the other collaborator is Carlos Jerez, also my former postdoc, now professor in Santiago in Chile. And as it happens, multitrace comes in two basic flavors, and these two flavors are also associated with these two gentlemen, as you will see. So, this project has other connections to France. In fact, I regard multitrace as the outcome of my most successful joint project with industry. Because at that time, there was funding by Thales. They were willing to spend money on the further development of boundary integral equation methods. And I happily seized the opportunity to take the money and start the research. Well, the research was very successful, so I'm very happy. The Thales people are not really happy, they are indifferent. Actually, when we then pursued all these exciting topics, they somehow lost interest. And well, in terms of science, it was a success. In terms of industrial outcome, I'm not so sure. But maybe things have to mature a little, and in the future, these new techniques will also be very useful for industrial simulations. Time will tell. So, what is it about? Let me start with an embarrassingly simple model problem, what I prefer to call a composite scattering problem. There's an incident wave hitting an object composed of several homogeneous materials. This can be an electromagnetic wave or an acoustic wave. We consider everything in the frequency domain. There's a fixed wave number, and then the propagation of the waves is governed by the customary equations. For acoustics, Helmholtz equation, and for electromagnetics, it's the frequency domain Maxwell equation. And the wave numbers are piecewise constant here in this model problem. And this is the key feature. You've got piecewise homogeneous materials, and we want to use boundary integral equation methods for the mathematical and then numerical modeling of this wave propagation and scattering problem. Well, between the domains occupied by different materials, we have to impose the usual transmission conditions. So we can think of the PDEs holding domain-wise, and then the connection is established by the transmission condition. Probably all of you know them. For acoustics, it's continuity of the solution and continuity, normal continuity of the gradient. for this simple model problem. In the Maxwell case, we've got similar transmission conditions. It's the tangential continuity of both the electric and magnetic field. Once we supplement everything with radiation conditions at infinity, the standard radiation conditions, because the exterior domain omega naught is also homogeneous, then we can take for granted, and this is well-established theory, existence and uniqueness of solutions. Solutions in a weak sense. So this is the model problem. It's, in fact, also a simplified model problem, because the methods that I'm going to present can also cope with non-constant coefficients in the second-order part of the operator. But for the sake of simplicity, I'm not going to address this. It's no basic limitation, however. Another remark, the methods I'm going to present, they're not really intended for very high frequencies. They are meant for medium frequency scattering. So the usual setting of, say, antenna problems. And the focus in the remainder of my presentation will be on acoustics. But I can tell you that most results carry over to electromagnetics with some additional technical complications, maybe. So, the plan for my presentation is to start with a very conventional, sort of standard boundary integral equation formulation that is widely used for this kind of scattering, or composite scattering problems. This is a first kind boundary integral equation approach, and I prefer to call it single trace formulation. It will turn out that this single trace formulation that is popular in engineering has a big drawback. After discretization, by means of lower boundary elements, it will lead to ill-conditioned linear systems where the ill-conditioning becomes worse and worse the higher the resolution of the boundary element mesh. Well, what one usually does is to apply a preconditioner to remedy this. But it seems that preconditioning strategies for this single trace formulation are a bit elusive. At least there's no really successful strategy available. And this was the actual motivation for studying alternatives. And the alternatives are the multitrace formulations. And as I've already hinted, they come in two flavors based on two completely different ideas. The ideas then converge in terms of formulations, in fact. First idea is a so-called gap idea, and it leads to a global multitrace formulation. And the second idea is, well, called a partial transmission idea or local use of transmission conditions, and it yields what I have dubbed local multitrace formulations. Two ways to switch from single trace to multitrace. And it's my goal now to explain to you the two ideas and the motivation behind the two ideas and what can be achieved by pursuing these ideas. These developments have not occurred in void. In particular, in engineering and also in mathematics, well, some people have pursued similar avenues. There's this boundary element tearing and interconnect method that is somehow related to multitrace And in engineering, from an algorithmic point of view, multi-trace type methods have been used for some time. These are the often advertised as integral equation domain decomposition methods. They are related, but they are not, well, they come in, of course, also in many variants, and some are more closely related. Some are a bit more remote from multi-trace. So, well, I was told I should gear my presentation to a general audience. So I will not take for granted that all of you are familiar with boundary integral equations and boundary element methods. And I hope this introductory part of the presentation will not bore you. So I'm going to give you a rather short but also gentle introduction to boundary integral equations. The details, the technical details are sometimes very difficult, but the general concepts are, I dare to say, fairly lucid. So we need a few ingredients to build boundary integral equations. And the main ingredients are trace operators, so operators mapping from functions in a domain to the boundary, and representation formulas. Let me start with traces. For our second order PDEs, there are two fundamental trace operators that all of you know. It's the Dirichlet trace operator and the Neumann trace, corresponding to this, the fundamental types of boundary conditions. Dirichlet trace is just point trace. And when you look at it from the perspective of Sobolev spaces, then the point trace can be extended to a mapping from H1 to H1 half. H1 half essentially the range space of the point trace operator. This is our first example of a trace space. This is known to almost everybody here, I suppose. Call this the Dirichlet trace space. And then we've got the Neumann trace, the conormal trace. And this maps into H minus 1/2, the range space for Neumann trace operator, the usual data space for Neumann data. Note the occurrence of the normal in the Neumann trace. So the Neumann trace depends on orientation. This will be important later. And there's another fundamental relationship between the two trace operators, or more precisely, the two trace spaces. The L2 pairing can be extended to a duality pairing between the two spaces. So they can be regarded as dual spaces of each other. And the duality is effected by a plain and simple L2, well, inner product or pairing. Will also become very important later, that you are very clearly aware of the L2 duality that is pervasive in the, well, for the spaces relevant for boundary integral equations. Second ingredient, representation formula. And representation formulas involve potentials. Here I've denoted them with the symbol psi. This is the single layer potential, psi SL. And the second is so-called double layer potential. Potentials take traces as arguments or functions from trace spaces and map them to functions in the volume. This is the most basic characterization of a potential. So, for the sake of brevity, I'm going to well, lump together these two potentials into one simply called psi. And also the two trace operators will be lumped into one just called gamma. And now, basic characterization of potentials. It's a mapping from traces, functions in trace spaces, to solutions of the PDE in the volume. So this is what a potential does. So plug in traces, you get a solution in the volume. And now the representation formula tells us that when you plug in the traces of a solution of the homogeneous PDE, of this one, so let U be a solution of the homogeneous PDE, then you recover exactly that solution in the volume. This is, you have a representation through potentials. This is why it's called representation formula. Potentials have representations as integral operators like this one, but we will never need this for the remainder of my talk. How these integral operators look like, all we're going to need are rather abstract properties, mapping properties of the potentials. These are integral operators with singular kernels provided by fundamental solutions and some derivatives, but these details don't really matter. So we have traces and potentials, and now we can combine both. It's as simple as that. You start from the representation formula. And then you apply the two traces to the representation formula, and the potential takes you from the boundary to the domain, and the trace from the domain to the boundary. So when you combine both, you end up with operators acting on traces and providing other functions on the boundary. And these are the boundary integral operators. Apply the traces, and this is what you get. Sorry. And then we can abbreviate the action of a trace on a potential by another symbol. Here I've called V, K, and W. These are the usual notations in the boundary integral equation literature. And these are boundary integral operators. They can be put together in this operator matrix. And now this is the kind of notation I would like to use. And I would like to introduce an even more compact notation. So this A, this compound boundary integral operator, it acts on a pair of traces. And such pairs of traces I call a Cauchy trace. So Dirichlet and Neumann together. And it returns another pair of traces. So we can also write it like this. And this is called a Calderon identity in its most compact form. So, and this is what I mean by not bothering about details of the operators. This compact form is essentially enough for presenting multi-trace formulations. So this will be the starting point. This Calderon identity, this identity for boundary integral operators. Everything is viewed from the point of view of Cauchy trace spaces, combining Dirichlet and Neumann traces into one, well, trace space, H1/2 and H-1/2 together. Here you can see it. And my symbol for this Cauchy trace space is just V. And so the operator A maps V again into V. It has many interesting properties. It's composed of the classical boundary integral operators, double layer, single layer, adjoint double layer, hypersingular, just to tell you the names. But the internal structure is not so important. What is important is that 1/2 identity plus A is a projector. And so A squared is actually a multiple of the identity. And A, or this, has other fundamental properties. And now the next one will be very important. When you have a pair of traces or a Cauchy trace in the kernel of this guy, then it will be valid boundary data for a solution of the homogeneous PDE. Because it's very important to notice that when you have Dirichlet data and Neumann data independent of each other, then generically they will not fit a solution of the PDE. Of course, because you can impose Dirichlet data, you can solve the boundary value problem, and then the Neumann data will depend on the Dirichlet data and vice versa. So it's only special pairs of traces that fit the solution of a PDE. And these special pairs of traces are characterized by belonging to the kernel of 1/2 identity minus A. And this is necessary and sufficient. Very important. Second very important property. The operator A is coercive. So you can, due to this L2 duality of H1/2 and H-1/2, it's obvious that V is self-dual. So you can just combine its Dirichlet and Neumann components in an L2 pairing, and then you get a self-duality. And this is meant by these brackets. And when you do this, then you obtain a coercive bilinear form in the sense of such an inequality. So it's elliptic up to compact perturbation in the Cauchy trace space. This is all we need to know about boundary integral operators. Fundamental results that everything will be based upon is the characterization of valid pairs of boundary data through this operator A, through the Calderon projector, and the coercivity property of the A operator. Now, let's take a look at the classical approach, the first kind single trace boundary integral equations. Single trace has to do with the functional framework in which these boundary integral equations are set. It's the single trace spaces. So, again, this is the kind of setting that I would like to start from. So you've got a number of domains separated by interfaces. Say, think of Lipschitz. Well, all of them are supposed to be Lipschitz domains. So sufficiently regular. Then the union of all interfaces I call the skeleton. It's just the union of all these black lines here. And now the single trace formulation lives in spaces of skeleton traces. So, what is this? Think of a solution of the acoustic scattering problem. This solution belongs to H1 globally, or H1 local on the whole space. You can imagine these functions as continuous functions, essentially. And then you restrict such a function to the skeleton. You get a function on the skeleton that, of course, has certain continuity properties inherited from the function in H1. And this function will belong to the skeleton Dirichlet trace space. And the skeleton Dirichlet trace space is the, well, can be defined as the trace space of global H1 functions on the skeleton. So you've got a function in H1 everywhere, restricted to the skeleton, and you get a function in this space H1/2 sigma. Similar construction for skeleton Neumann traces. take a solution, compute the gradient. The gradient is a flux field. It's divergence conforming in H-diff. And now you can regard this as a global H-diff function and take the normal component trace on the skeleton. And this gives you a function in H minus 1/2 sigma. So the traces in these two single trace spaces or skeleton trace spaces are intimately connected to functions defined globally. And this, of course, means that, for instance, for Dirichlet traces, you have a single value on each point of the interface, sloppily speaking. The orientation here does not matter that much. Well, when you've got a global flux field, then you can just impose an arbitrary orientation on each interface. And this is the normal direction that you consider on that interface. And this is what you use to compute the function on the interface, the normal component trace. So when you flip the normal, the sign will change, but it will still be the trace of a global H-diff function. So you can fix the local orientation. So this is what I've indicated with these normals. You can fix them in an arbitrary manner, and you will always end up with essentially the same space. So the orientation in the definition of these spaces does not really matter. It has to be fixed, but it can be done so in an arbitrary way. What this perspective gives us is a localization method. Since these skeleton traces are closely connected to global functions, you can also consider the trace of the global functions subdomain by subdomain. For instance, take omega 2, you've got a global H-diff function, so you can consider its trace on the boundary of omega 2, of course. And this gives us a natural localization operator. So when we have a skeleton trace, we can intermittently switch to this global function, take its local trace, and this gives us a trace function on the boundary. So we have these localization operators. Let's call them Li. Clear? I want to make sure that everybody can follow at least the intuitive ideas.
Just to be sure, for example, between L1 and L2, I will change the sign of the...
Yes. When you look at it from the point of view of functions, and this will then come on the next slide, then there are sign changes. Be patient for a few seconds, because now I would like to give you some, say, discrete picture of these trace spaces, single trace boundary element spaces. Because it's my point of view that sometimes, well, going to a discrete setting gives valuable insights. So let's look at it from a discrete setting. What is a single trace space in a discrete sense, in the sense of boundary element functions? Let's look at this setting, a split disk. Simplest case, so we want to discretize this Dirichlet skeleton space. And we want to use piecewise linear boundary elements. And remember, these have to be traces of functions in H1, so they have to enjoy some continuity. And it turns out that we have to impose continuity, like for finite elements. So, and then we equip the boundary with a mesh, and then, well, the natural single trace boundary element space would be piecewise linears that are continuous, say, at these junction points and have a unique value at all the other points and linear in between. And for the Neumann skeleton space, what you would do is you would use piecewise constants. This is a simple scheme on the same mesh, and each cell gets a value. And now, of course, these values depend on the orientation, on the arbitrary orientation. So you fix an orientation here indicated by the arrows, and then this cell value gives you the flux from here to here. If you flip the orientation, then of course you have to change the sign. So this is a discrete picture of single trace space. And now, this is the space in which the single trace formulation lives. So remember this localization operator, and now I've really put in the sign here on the Neumann data depending on the orientation. Now this is the function point of view, or the trace point of view. So you take the Neumann data and look at the orientation, and in case you have to flip the sign. And now how does the single trace formulation look like? It's surprisingly simple. We start from the fundamental result that when you solve the scattering problem, then its Cauchy trace is in the kernel of this operator, subdomain by subdomain, everywhere, in all subdomains. And now I've written phi here for the skeleton trace of the solution. So Dirichlet-Neumann, and the localization operator just gives the subdomain trace of the solution. So this is really another way, or an immediate consequence of the characterization theorem for Cauchy traces. And now let's just add all these zeros, or not exactly zero, because there's an incident wave which enters the right-hand side, but this is what I sweep under the rug here. Let's add all these equations. Of course, this is a bit problematic because they operate on different spaces, because this maps into the local trace space. But what we can do is we can just put the adjoint of the localization operator here, because then we map back to the skeleton space, more precisely to its dual. And so what I've written here implicitly is already a variational formulation. So this takes a function in the skeleton space, and finally it maps back to the dual of the skeleton space, and so it's a natural variational formulation. And then there's a trick. This mysterious identity holds. But this is not really mysterious. Why this? Well, casually speaking, we integrate, when we switch to the variational formulation, over each interface twice. The Dirichlet data have the same value from left and right, and the Neumann data have the same value but with signs flipped. And so on each interface, everything cancels when you evaluate this. And so this can be dropped, the identity can be dropped, and this comes out. And this is the single trace formulation. And this is beautiful in mathematical terms, because this operator induces a coercive bilinear form. Why? Because we have coercivity of all these AIs. This was one of the fundamental property of the A operator. And this is just adding coercive operators. And so the coercivity will be inherited by the sum. Existence and uniqueness holds. And this is beautiful theory. This is well established for both acoustics and electromagnetics. Here in these two papers, you find the mathematical analysis. So then, the bad news, this is a first-kind formulation. In these A operators, you have operators of order 1 and -1, to be precise, when you look at it more closely. And so when you discretize by means of low-order piecewise polynomial boundary elements, the same happens as in the case of H-version finite elements. When you refine the mesh, then the conditioning of the discrete linear systems will blow up. It can be quantified like h to the -2 as you refine the mesh. This is a serious drawback. Why? Well, also in the field of boundary element methods, people nowadays compute with 1 million unknowns. When you want to deal with 1 million unknowns, then you have to use matrix compression for the Gajerkin matrices for this formulation. This is also well known. There are efficient techniques available, but matrix compression forces you to use iterative solvers, GMRS, CG in simple cases. And the iterative solvers will suffer tremendously as you refine the mesh. The convergence becomes slower and slower. And so this has become a headache.
Maybe just a question. For a standard exterior problem, the conditioning is h to the -1. Usually.
Yes, because...
Due to the fact that you have a transmission problem,
yes.
and you have the combination of the two.
Exactly. For a simple Dirichlet or Neumann problem, you've got only one of these operators, either W or V in the first-kind equations, and then the condition number increases like 1 over h. But here both are present, they have opposite order, and you observe 1 over h squared. So this is a serious problem for the use of this first-kind single trace formulation. It's very nice, but this is its, well, main drawback. Well, remedy, preconditioning. Very simple case. Single interface. Then the skeleton trace space is very simple. It's just the Dirichlet trace space and the Neumann trace space together on this closed boundary. Clear? Now we have the skeleton is just the boundary of omega 1. All right. And then for this simple case, this is the first-kind single trace formulation. You see, we just sum after localization these A operators for the two domains, for the exterior and the interior. And when you rewrite it in terms of atomic boundary integral operator, it looks like this. So this is now, in this simple case, there's a very effective preconditioning strategy available. And it's can be called operator preconditioning, often known as Calderon preconditioning. It's a very general strategy. So there's an abstract theory. You have a space and, say, finite dimensional subspaces, two of them, VH and VH tilde. And then you've got two operators associated with bilinear forms with variational problems, A and B. And you apply Gajerkin discretization of both. based on VH and VH tilde respectively, and we assume that this is stable, independent of H. And then another key ingredient. You have to assume that you've got a discrete duality pairing between the two boundary element or finite element spaces. And this means that this bilinear form D is insubstable on the pair of, well, finite element spaces. If you have this, then it's not really difficult to prove that the condition number of this matrix product, kappa stands for the spectral condition number, and this can be any Gajerkin matrices that arise from A, B, and D. Just choose any basis for the spaces and then plug them into the bilinear forms. And then you have this bound. And now if the finite element spaces do a good job, if the discretization is, stable in this sense, then you've got this estimate for the condition number. And, well, these norms are in fact, well, this is, for instance, the inf sub constant, 1 over the inf sub constant for the D. So these norms are related to inf sub constant and continuity constants for the discretized operators. And this is operator preconditioning. So it's a very abstract framework. And this has turned out to be an extremely powerful technique for boundary integral equations and boundary element methods.
What is a capital H?
This is the Hermitian conjugate, Hermitian transpose, sorry. Just because these are matrices now. The bold symbols designate matrices. So just the Gajerkin matrices. So, and for the single trace formulation on a single interface, this is an excellent technique. How can it be applied? This is the space V. The space V is self-dual. So V and V prime are essentially the same, and the duality is given by L2. So the D here will just be the L2 pairing that induces the duality of the Cauchy trace space. And what are the operators? Well, the operator is just the operator of the single trace formulation. Because this operator maps from V to V prime, and V and V prime are self-dual with respect to L2. So we can choose A and B as the same operator. We can precondition the single trace operator by itself. Sounds strange. Well, but this is what you get out of this theory. It's not so strange, because remember what we had. We had for the A operator that A square is a quarter times the identity. And when you multiply the operator A with its, or the single trace operator with itself, you get something similar. You get a compact perturbation of the identity. And so it's not so surprising that the operator preconditions itself. And this, now, as VH and VH tilde, you choose boundary element spaces. There's one complication, and the one complication is that you have to be very careful about inf substability. For instance, when you have H1 half, discretized with piecewise linears, h minus 1/2 discretized by means of piecewise constants, then you cannot just form an L2 pairing and hope that it's stable. Because to begin with, these spaces will usually have different dimensions even, and then finite dimensional spaces have to have the same dimension as a necessary condition so that you've got a stable pairing between them. So what has to be done is so-called dual mesh techniques. For instance, you have to use piecewise constants on a mesh whose cells look like this. This is a vertex, and this is then a cell of the dual mesh, and there you use piecewise constants. So you got an agreement of dimensions, and then an inf-sub stable L2 pairing is possible.
Sorry, I missed something. Why, to apply your abstract theory, you need that A and B are each uniformly stable? And so you said that why it is the case for?
Well, this is a consequence of the coercivity. So they are H uniformly stable, of course, with respect to the V norm. Remember, the blow-up of the condition number of the Gajerkin matrices has to do with the intrinsic instability of the boundary element basis in the energy norm. But the discrete operators are perfectly stable in the energy norm. So there's no contradiction. So in the V norm, the discretization, the discrete operator here, the discrete boundary element discretization of this guy is perfectly stable. But in the energy norm, whereas the boundary element bases are usually stable only in the L2 norm, and there's a gap. Is this? Yes, this is a sort of a challenge here to understand different concepts of stability that come into play. This stability here, this invariably refers to the norm in V. And this was the H1/2 and H minus 1/2 norms. So we can use these techniques for preconditioning. And this is also well developed. And now what is the problem in the general situation? Say, two domains. We have the single trace formulation acting between these spaces. And there's L2 duality. We know as a stable duality pairing on the continuous level and the discrete level. On the skeleton, we have no idea. L2 duality does not work on the skeleton. The L2 pairing in the skeleton space is not a valid duality pairing. But L2 duality is crucial for applying the operator preconditioning. And so we cannot apply it. As once there is a single junction point where several subdomains come together, it doesn't work anymore. And this is still open, how to do operator preconditioning in skeleton spaces. So this was the starting point for seeking formulations that are more friendly to operator preconditioning. What is the idea? The idea is essentially a domain decomposition idea. The idea is to return to a setting where you have this L2 duality by tearing apart the skeleton traces, switching back to localized traces. So we now marry boundary element methods and domain decomposition. So we want formulations that are posed in local spaces, because there we have L2 duality. And now, when you have this space, then on each interface, you have a traces from left and from right. You have more traces than before. And this is what has earned these methods the name multitrace. First idea, gap idea. I've dwelt on the single trace formulation a long time because the gap idea, well, naturally builds on top of the single trace formulation and gives rise to the global multitrace formulation. So what is the idea? Let's consider the single trace formulation for this setting, separated subdomains. Of course, the single trace space is very simple. Again, it's just the Cauchy traces of omega 1 and of omega 2. And here we have a nice L2 duality pairing because, well, these are just trace spaces on the boundary of a subdomain. This is the single trace formulation. And what I've written it split with respect to the two subdomains. So you've got the A operator, the local A operators, and you've got coupling operators between the subdomains. I call them R for remote coupling operator. Why remote? Because it takes a potential on one subdomain and then forms its trace on the other subdomain. So this is why it's remote coupling. And now there's a key observation, and I credit it to Xavier. He noticed that when you think of a small separation of these subdomains, you can let the gap shrink to 0 and nothing happens. All the traces, all the operators are not affected. So we can formulate the single trace formulation without any change for delta equals 0. So this is why this is called the gap idea. You start with a virtual gap and then ignore it, and it turns out everything remains okay. And this is now the picture after closing the gap. And now you see why it's multitrace. In the single trace formulation, indicated by this magenta line, these are the boundaries that carry unknowns, that carry the two unknowns, Neumann and Dirichlet data. And now when you close the gap, then you see here at this middle interface, you've got functions from left and right. You've got 4 unknown functions, two traces from left and 2 traces from right, multi-trace. And this is the idea. Now you can do this for many subdomains. You introduce virtual gaps, close them. First formulate the single trace formulation. And then, of course, the final formulation will be posed on this simple product of spaces. These are just the subdomain Cauchy trace spaces next to each other. Nice L2 duality here, no problem. And when you discretize, now again I would like to switch to a discrete picture, then what you do is you first think that these two halves of the disk in this setting are separate. You separately mesh them, you introduce, say, piecewise linear continuous functions on both, and then put them together. And this is the boundary element space for this multitrace formulation. No relationship whatsoever stipulated for the interface. So you can have different meshes as indicated here. Completely separate. And the same for the Neumann data. So now you've got Neumann data from left and right, Dirichlet data from left and right on the interface. You've got more unknowns, but the benefit is now you have decoupled traces on the subdomains, and you have a natural L2 duality of self-duality of the space. And the great thing is that since we started from the very stable classical single trace formulation with a beautiful theory, and we found that closing the gap doesn't destroy anything, all the theoretical properties remain intact. This operator will be, as the single trace operator, will be coercive in the trace space, existence, uniqueness of solutions, and nice convergence theory for boundary element methods. So this was very satisfactory. And this is the global multi-trace formulation. It also works for electromagnetics, very similar. And operator preconditioning, now it's straightforward. You do locally what you did for the single trace formulation for the single interface. Dual mesh preconditioning, for instance. Now, this is a simple numerical example. So essentially, again, the operator preconditions itself and the L2 duality in between. Simple 2D experiment. I think the wave numbers were 1, 2, and 3 in 3 subdomains, so split disk setting. Sorry. Oop. And this is what you get. Experiment by Xavier. GMRS behavior. This is the non-preconditioned case, multi-trace, single trace. You see, well, rather slow convergence. And this was the GMRS convergence after operator preconditioning. And what you also observe is that this is perfectly robust with respect to mesh refinement. When you refine the mesh without preconditioning, the number of iterations blows up. With preconditioning, it essentially stays constant. Great success here. But in the beginning, we were not so sure, so that in parallel, Carlos looked at another way to do multi-trace. Different idea now. Let's again look at the simple setting. U is the solution of the scattering problem. This is essentially local Cauchy traces. So for each subdomain, you've got Dirichlet-Neumann trace. And then we have already seen these identities. This is the characterization of valid pairs of boundary data through the Calderon projector. Again, the starting point, as with a single trace formulation. Okay, here in this setting, you have these 3 equations. And now, well, at first glance, we are going to do a crazy thing. We start from these equations. And we replace this part of the operator, this identity times the traces, with the traces from the other side using the transmission condition. So here you see this, say this gamma 1, the Cauchy trace, now has, on subdomain 1, is now replaced with the trace from subdomain 0 on this interface and with subdomain 2 on this interface. Of course, you cannot simply do this. You have to do it through an operator, and this is this X, the trace transfer operator or transmission operator. What does it do, this X? This X takes a trace from one subdomain, restricts it to an interface, copies it to the other side, flipping the sign of the Neumann data in the process, of course, because this means a change of orientation, and then extends by 0. So this is the transmission operator. And now these transmission operators are used to replace these second parts of the Calderon identities. Crazy idea. because you start from disconnected equations and then you use the transmission conditions partly. The unknowns, of course, are now traces on all the subdomains. Again, multitrace. On each interface, we have traces from left and right as unknowns. And this is the structure of the resulting operator equation, again written in our compact form. You've got the local A operators here. These are the classical integral operators. And then coupled through the trace transmission operators. But what we've achieved, again, is a complete decoupling of local traces, so a perfect environment for doing operator preconditioning. And this was our hope when we started looking at this idea. Well, there's a subtlety here, and which gives us a lot of theoretical headache. You notice this tilde. The trouble is that these trace transfer operators do not really make sense as operators on the trace spaces. They are not bounded there. Because for Sobolev spaces with half-integer indices, these are the most awkward Sobolev spaces, in fact. Just extension by 0 is not a bounded operation. It's not valid. And also cutting or restricting to an interface is not, well, such a good operation. So what we observe that these transmission operators are not well defined on the trace spaces that we would like to work on. So we have to switch to slightly more regular test functions, and this is what is indicated by the tilde. The tilde has to do with the so-called tilde trace spaces on parts of a boundary. So these are subspaces of the trace spaces where extension by 0 is not problematic. But they have other, well, difficult aspects. So I just would like to point out that this is a main theoretical challenge here. This formulation is not so meaningful in the setting of natural trace spaces. But a lot can still be done. And this starts from a key observation. This starts from the observation that this operator has a very nice structure. It has a coercive diagonal, and at second glance, one notices that the off-diagonal blocks are skew-symmetric. And when you have a coercive diagonal and skew-symmetric, well, off-diagonal, then you can expect some coercivity of the total operator. And this is, in fact, true here. So this, the bilinear form used by this multitrace operator is coercive. Well, there are technical difficulties because the continuity, again, is a bit problematic due to the unboundedness of the transmission operators. But with a lot of technical effort and based on a result by Pierre-Louis Lions, we could do it. We could show that this is a well-posed formulation with existence and uniqueness of solutions are guaranteed. And then also show some convergence of boundary element discretization. So far in 2D, well, assuming some elliptic regularity for a transmission problem that we have not yet bothered to establish rigorously, but it looks very natural. So, also this formulation is well posed, very nice. And it's posed in a setting perfect for operator preconditioning. Again, this is the operator, and we could precondition it by itself, but we can also precondition it by its diagonal. This is what we usually did. And use local L2 pairing for the D. And then what you get is very impressive results. Now, these are results by Carlos in 2D. Again, the split disk case. These are 3 different meshes, dashed line, no preconditioning. GMS convergence deteriorates, and solid line with preconditioner, well, no significant deterioration. We expect a little deterioration logarithmic in H. This is what comes out of what we conjecture and what, well, can probably be proved. So now we have 2 multitrace formulations, global versus local. For the simple setting, these are the operators. The global is very nice in terms of theory. There, everything is established rigorously and well known. Convergence of boundary element methods in energy norms is done. But, well, we've got these remote coupling operators, and they also, of course, have to be discretized. And they are non-local. No? Come on. Well, dense matrices here for R. For the local multitrace formulation, it's purely local coupling across interfaces. So the discrete transmission operators give rise to sparse matrices. For both, operator preconditioning works well. In terms of accuracy, what we see from numerical experiment is that they are competitive.
I have a question. The matrix, the operator A1 and A2, are they the same in both formulations? Or
Yes.
They are the same?
The same, yes.
Okay.
Exactly. So these are the classical integral operators confined to one subdomain. So what you need when you implement these methods is a machinery that gives you the discretization of classical boundary integral operators on the boundary of a domain. Then you can combine them into these more complicated operators of the multitrace formulation. So in experiments, we observe a comparable accuracy, also comparable to the accuracy of solutions of the classical single trace formulation. So here, no hidden drawback. That's all I wanted to say, essentially. Few final remarks. We've got 2 multitrace formulations. The big benefit is now they can be preconditioned very effectively. For local MTF, there are quite a few open theoretical problems. Say 3D convergence and, well, also electromagnetics, partly open, because in particular for the boundary element analysis, you need inverse inequality and you need approximation estimates that can be very subtle due to this extension by 0. Well, another interesting issue which Xavier is pursuing is, can these formulations be extended by using other transmission conditions? Well, they say in the sense of optimized Schwartz iterations. So some people, including Xavier, have recently done, first steps in this direction. Still, much is open. And, well, if you're interested in proofs, details, then you may look at these 2 survey papers that give a rather comprehensive presentation of the multitrace formulations. But I hope also this presentation gave you some idea of what multitrace is about, why we were interested in this class of methods, what the big advantage is, and, well, what kind of ideas underlie them. That's all I wanted to say. Thanks for your attention, and thanks for your patience, because it took a rather long time.